Have you ever looked up at a massive concrete skyscraper and thought, what is actually keeping this thing from just tumbling down? Well, welcome to this explainer. Today, we're diving into what I like to call the ultimate high-stakes recipe. You know, in baking, a bad recipe gets you a flat cake. Disappointing, but not a huge deal. But in construction, the exactness of the ingredients and the absolute microscopic control of their quality literally means the difference between a building standing safely for millennia or catastrophically collapsing.
Now, ancient statues, like the ones at Abu Simbel, were definitely built to stand the test of time, and they absolutely have. But let's be real. Back then, construction relied on incredibly heavy, dense materials and, honestly, a whole lot of trial and error. Today's modern structures are way taller, much lighter, and infinitely more complex. Builders today just do not have the luxury of guessing. Instead, the industry relies on precise, rigorous scientific testing to guarantee that our skyscrapers and bridges can outlast even the greatest monuments of the past.
So here's the exact recipe we're going to unpack today. First, building to last. Then, cement, the crucial binder. Third, aggregates, the rock-solid core. Fourth, water and chemical additives. And finally, putting it all together in the perfect control mix. Let's get into it.
Starting with Section 2, cement, the crucial binder.
Okay, because cement is essentially the glue holding this entire massive recipe together, builders can't just grab any random powder off the shelf. The cement type has to be exactly what's specified for the project, and the manufacturing process has to strictly follow really rigorous standards, like ASTM C183-8. And here's a wild fact for you. The specific surface, which is basically a scientific way of measuring how fine the cement powder is, has a massive impact on its compressive strength over periods of 7 to 90 days and even up to a year. Basically, the finer the cement, the stronger it gets over time. To guarantee this microscopic exactness, testers actually sift it through a number 170 sieve. This thing has tiny 90-micron openings. If more than 10% of ordinary Portland cement by weight gets left behind in that sieve, the entire batch gets tossed out, no exceptions.
Once the powder passes the finest check, it faces its very first real torture test. Using this really fascinating tool called a Vickett apparatus, testers mix exactly 400 grams of cement with exactly 100 millimeters of water. They take that paste, stick it under a specialized needle, and then they literally just let that needle drop into the paste every 10 minutes until it completely stops penetrating.
So, what are they actually looking for with the dropping needle? Setting time. The initial setting time absolutely cannot be less than 45 minutes for almost all cement types. Why? Well, think about it. The construction crew needs actual physical time to pour and work the wet concrete before it chunks up. But on the flip side, the final setting time can't take longer than 10 hours. The mixture has to harden eventually, right? Otherwise, the entire massive project just grinds to a halt.
Finally, the cement goes through a brutal crushing test. Technicians mix the cement with sand in a 1:3 ratio, add a very precise splash of water, and mold these perfect 70.7 millimeter cubes. Then, they take those cubes and literally crush them in a powerful hydraulic press. And the standards are unforgiving. Ordinary Portland cement has to survive 18 newtons per square millimeter of pressure at 3 days, 27 at 7 days, and a whopping 36 at 28 days. It's a rigorous way to prove, without a doubt, that the material is reliably gaining the strength it needs over time.
Moving right along to Section 3, aggregates, the rock-solid core. So if cement is the glue, aggregates are the muscle. They provide the structural mass that makes up the bulk of the concrete. To guarantee ultimate quality, these rocks and sands are physically sorted by size using a tall stack of progressively smaller sieves. But there are also invisible dangers, so they use a really clever on-site test. Testers take pure water, add the sand, shake it aggressively in a tube, and just let it sit for 3 hours. The heavy sand naturally sinks to the bottom, and any fine problematic clay materials settle right on top. It instantly exposes the bad stuff that could silently ruin a mix.
But hey, shaking and sifting isn't enough to guarantee real structural integrity. Enter the Los Angeles Abrasion Test Machine. This rotating steel cylinders where coarse rocks face their ultimate punishment, to see if they're genuinely tough enough to make it into the recipe.
Here's how it works. A washed and dried sample of the rocks goes inside the cylinder, along with heavy steel balls, sometimes up to a dozen of them, depending on the grade of rock. Then, they spin the machine 500 times. It is violently loud in there. It's essentially a giant metal blender for rocks. Afterward, they take the resulting wreckage and pass it through a 1.7 millimeter sieve. They wash, dry, and weigh whatever survived. If those rocks lost more than 20% of their mass to that brutal beating, they completely fail.
Going back to that clay test for a second, it really all boils down to the weakest link. Even a tiny, tiny fraction of a percent of clay can fatally compromise the aggregate strength because it stops the cement from actually bonding to the rock. The limits are crazy strict. A max of 3% fine materials in regular sand, 5% for crushed stone sand, and a microscopic 1% for coarse aggregate. If it's even a fraction over that, the recipe is pretty much doomed.
Section 4. Water and chemical additives.
So we have our binder and our rock-solid core. Now we need water and chemical additives to activate the whole thing. But just like invisible clay, dirty water ruins strong rocks. The water used in this kind of construction must literally be safe enough to drink. Total dissolved solids can't go over 2.0 grams per liter, and things like chlorides and sulfates are capped at absolute microscopic levels. Why? Because if the water's too salty, it's going to silently rot the internal reinforcing steel from the inside out, long after the concrete is already hardened.
Now, sometimes we do need a little chemical help on a job site. Maybe retarders to slow down the setting time on a sweltering summer day, or water reducers to make the concrete flow nicely into complex shapes. But these additives are heavily tested. You can't solve one problem while subtly creating a new one. The concrete's compressive strength is retested at 3, 7, 28 days, and even 6 months out, just to guarantee that these chemicals haven't unexpectedly dropped the structural strength compared to a standard, unaltered batch.
And finally, Section 5. The perfect control mix.
Once every single ingredient has survived its respective torture test, it's time to bring it all together into the master recipe. We call this the control specimen. This is a masterpiece of exact, meticulous ratios. We're talking exactly 300 kilograms of cement per cubic meter, with a cement-to-aggregate ratio of exactly 1:6 by weight. Even the sizes of the rocks are perfectly blended to lock together like a puzzle. 45% large rocks, 20% medium, and 35% fine sand. With the water strictly tuned and trapped air kept under 3%, it becomes a perfectly balanced, scientifically validated supermaterial.
So as you can see, concrete is definitely not just gray mud that dries hard. It is a heavily scrutinized, highly scientific combination of relentlessly tested ingredients. Do me a favor, look around the room right now. Think about the walls surrounding you, or the floor beneath your feet. How many violent abrasions, crushing pressures, and microscopic inspections did the very building you're sitting in have to pass just to keep you safe? It's kind of wild to think about, right? It really gives you a whole new appreciation for the hidden science supporting our everyday lives. Thanks for hanging out with me on this explainer, and keep questioning the world you're built upon.